Okay, some of the things first. For the exam purposes, we will, of course, we allow you to bring your calculator, and if you have a graphic calculator, some of the probability calculations, especially from specific binomial or Poisson or normal or some others, will be using your calculator. But then to cater those that you don't have a graphic calculator, this is the table that we will attach. We will tell you a little bit more about the format of the question paper, but at the end of the question paper, we will insert some of this table for those who don't have the graphic calculator. And in the coming tutorial questions, we will set some samples of this type of questions, so that sort of having you to practice it. But we will bear in mind that some of you don't have a graphic calculator, so the question paper will be set in such a way those who don't have a graphic calculator will not suffer too much disadvantage. For a lot of problems, I guess you can just handle it by hand. You don't need to use a calculator. All right, and then there is another file that we uploaded, is the statistical table. For those who are interested how to create your own table using Excel, you can learn something from here. So if you click on some cells, they actually give you the formula how this number is generated from the Excel function. So even if the table may not be of interest, but it would be of interest to learn how to do it. And then we also, this is the binomial for different sheet, and then this is for Poisson. You will see, actually the book is still available in NUS in CloseDeck, and now the book actually is available in PDF file, electronic file, that was published in 1953. It's a book, and the book basically gives you pages and pages of different n. So this is n equal to 20 for this table, and then for different p. And just pages and pages of this. This is actually provided, if I remember it correctly, is by the Institute of National Institute of something like Standards and Technology. So, but that was very useful at that time. But of course, it's getting outdated. And then you also have the normal. All the probability here are given. I will emphasize it when we come to it. All the probability here are the upper tail probability. So this is something you need to be aware of. And so the first thing when you see a table, you would need to read the caption of the table. Here is the title here. What the numbers are representing. This is always a good practice. Now, of course, most of the table that you are reading would be conforming to this kind of good practice. But in the future, when you create your own table, you need to explain what the numbers are for. All right. So this is something that you need to cultivate a good habit of doing this. You don't assume the reader know what the numbers are representing. Now, this binomial distribution table is giving you the upper tail only, and then for point probability, you need to do subtractions of consecutive numbers at the right place. And then if you need the the lower tail probability, you have to do 1 minus of this. So it's a little bit troublesome, but that is how life was many years ago. So this is the chi-square, and these are the different rows are for the different degree of freedom. And chi-square is basically used, at least in our module, for hypothesis testing or confidence interval constructions. So we are only interested in some particular numbers, all right? Basically, they are quantiles, all right? So 99.5%, 99. Now, the 99.5%, let me repeat it again. It is the upper tail. So if the upper tail is 99.5, that means the left tail, the lower tail is only 0.5%. So you have to watch out for this, all right? And this is why it is arranged in this order, all right? Because the number is in increasing order here. We will have some explanations. And then this is the T distributions, the famous T distribution. This is very well studied. This is actually, the paper was published in 1905. The table is, of course, not available in this generality. The table, it is called a student. When we come to it, we will explain why the name of the author is called student. And then this is the F distribution. F distribution has 2 degrees of freedom. So as a result, this is the first degree of freedom. I mean the columns, and then the rows are the rows are the second degree of freedom for the F distributions. And this is each row will correspond to different alpha. And again, this is basically used for hypothesis testing. And we are interested as testing things at 5% level, or 2.5 if we have 2 tails, or 1% here. So when we come to it, now of course I have mentioned a number of times that this is how it is generated, and of course this can be replaced by an online calculator as well as your graphic calculator or the software, any statistics software. All right, so so the main emphasis nowadays is not how to get specific numbers. That probably might be just one tiny step. And the thing is to understand the statistics implications and the thinking. All right. So, but before I do that, I want to give you an overall picture of this module. So this module actually will consist of 7 chapters. Chapter 1 to 4, you can think of it as probability. So the probability, you can either think of there is a population, or there is a process or generator generating outcomes. The generator we are thinking of is flipping the coin. Suppose we flip it 10 times, so the generator will flip the coin 10 times and tell you the numbers, I mean the 10 outcomes, and so on. So the concern is to, everything is known about this. All right? So this is the main difference. Everything is known, and then the thing that we wanted to answer is the proportion, or in our word, is probability of something. Suppose we are talking about height, so we are interested in certain proportion of people exceedingly tall, because when you are designing houses or many other things, you have to take into consideration of this. A lot of bed now in U.S., is no longer 6 feet long. It's longer than 6 feet because people are taller now. Years ago, in IKEA, even in Singapore, you can buy what they call a super single. So the bed is a bit longer and a bit wider. Unfortunately, they stopped doing this. I mean, they stopped this production. At least they stopped the sale in Singapore. So, I mean, knowing certain proportion is important because this will affect the kind of product that you are going to do. So the thinking is we know everything about the populations in terms of the distributions. And so we are interested to answer certain particular questions, all right? And so this is what it is about. And then for chapter 5 to 7, this is more like the statistics. Again, we are interested in the populations. But in the populations, we do not know enough, all right? But we need to know something, otherwise we wouldn't be able to answer certain questions. So this is what we assume to know. All right, in the slide it will mention it. We assume we know the form of the distribution. Okay, example, we know that it is normal, all right? But we do not know these parameters. This parameter is unknown to us. All right, so we sort of like a compromise. We assume we know something, but we do not know the entirety of the whole thing. Whereas in here, not only we assume we know the distribution, but we also know the parameters, the mean and the variance here. And we answer this kind of questions. So we wanted to, the first thing is basically we still want to answer this type of questions, but we are not able to do this because the distribution is not completely specified. So the first step is in statistics is to find out these parameters. Okay, so this is statistical inference. Okay, and there are basically two big types or three types. One is called estimation. All right, and the estimation we are going to introduce, you can think of it as either a point estimation. You wanted to estimate the value of the mean and also the value of the standard deviation. All right, so you want to give a number for the mean and a number for the standard deviations. Another thinking would be, I don't want to be so precise. I want an interval to say that the numbers are likely to lie inside the interval. So this is called interval estimation. The confidence interval is what you are familiar with. And of course, depending on the context, most of the interval is a two-sided interval, meaning that you have a lower bound and upper bound. But in some questions, all you want is some lower conservative, a conservative estimation. You don't mind about you might overestimate, but you wanted to really don't want to underestimate certain things. Then you might be interested in a one-sided confidence interval, all right, and so on. And then another type of statistical inference that this will be covered, I think, in chapter 6. And then is the decision making. Of course, there are many types of decision making. The type that we are studying would be hypothesis testing. All right. We are interested to test whether the mu is of a certain number. Talking about the height, we are interested to test, say, the height of, say, the young people nowadays, maybe to be more specific, people who are in their 20s, as compared to, say, 10 years ago of Singapore, which is known, or which is already estimated long ago, whether the young people nowadays are taller than their counterparts 10 years ago. Could it be due to better nutrition or other things? So we are interested in testing no longer, suppose I have a particular number. I no longer wanted to estimate this, but from the data, I wanted to say something. I wanted to have a more like an adversarial kind of a thinking. One says that the meal is equal to the previous 10 years mean, and then the other say, no, they are different, all right? Now, this is just one form, or in the height that I was referring to, it might be more meaningful to talk about this because I'm interested to test whether generally the people in the 20s nowadays are taller than their counterparts 10 years ago. All right, so this might be the alternative. Another thing, of course, I don't think we are going to do it, is prediction. Some of the things that you learned are regression. And other thing is to, if I already have a particular sample and now I have a new data, can I predict something about this guy? A lot of these situations is in medicines or in other things. Suppose I am able to measure some of your characteristics, say blood pressure, heartbeat. Your pulse rate, your blood pressure, your age. Suppose I can measure some other biomarkers in your blood. Can I predict how risky you are for a certain disease? All right. Now, this is just everywhere, this kind of problem. For example, a recent one that I came across is the deep vein thrombosis. Most of the situations they wanted to see, based on some measurements of the biomarkers that they're measuring, they wanted to see whether the patients just need to be watered and then being observed. They are not going to do anything because this is low risk. But if it is high risk, they might want to do a bit more aggressive way to treat it. So again, this is some kind of a prediction. Now, so back to what we are wanting to do. So to answer this, we wanted to draw a sample. Now, sample as a contrast to the other one is a census. All right, so you measure everyone in the population versus you only measure a few. If you really want to be serious, the few may be like 2006 or 2005, usually the recommended one. And then the census is you measure everyone. Now you might have, now of course if I measure everyone, there are advantages of measuring everyone because then I don't need to do estimate. All right. I simply calculate the mean and the standard deviations of everybody in the populations. But there are two things against doing a census. First of all, it is extremely costly. Okay, and also by the time you finish it, things might change because it might take some time to do so. And another thing that is against census, this is the most important thing, is in a lot of measurement, you might destroy it. For example, in drug, if you want to test, a consignment that you nab it from someone, you suspect this contains a certain proportion of drugs. If you are going to test everything, now there is some reason they don't test everything. If they test everything, then everything will be destroyed. Now, if the defense wants to argue certain things, they have no longer the things to be redone. Okay. Another thing is, for example, you are interested in the matches, whether the proportion of the matches that work. If you test everyone, then what's the point, right? So you destroy everything. So especially when you are doing destructive things, when you're measuring it, you destroy the things. So you then sample is the only way to go. You can't test everyone, because you will destroy everyone. Okay, so this is why we wanted to do sampling. Now, another advantage versus census is if I only measured 2006 or 2005 versus, say, the entire population in Singapore, which is about 5 million, for maybe even 20% of the resources or even 10% of the resources, I can measure this 1,500 people or 2,500 people in a much more precise way. I can look at the I look at the individual measurement much more. I can measure everyone few times and then take an average. And so my measurement for each of the subjects in my sample would be much more accurate than I measure everyone. And in that case, because of the resources, I can only measure one, in a very rough way. So, so this is where sampling is. So we denote two things. Populations and sample. The aim of statistical inference is to say something about the populations based on a sample. We often know that the population belongs to a known distribution. So this is this is often means a little bit. Should be in quotation mark. But we are willing to assume the populations has a certain form of distribution or belongs to a family of distributions. But in order to know the distribution exactly, I have to tell what are the parameters of this distribution is. In the normal distribution, I need the mu and the sigma. In the binomial, I need the p, the proportion. In the Poisson, I need the lambda. Okay, we might be willing to assume that it is Poisson. Say, for example, number of accidents, number of typo mistake on a page or in a book. So we usually model it as a Poisson, but it might vary from person to person, or it might vary from publisher to publisher. So we need to know the parameter. Okay, a poster is sure that the responses to his agree or disagree questions will follow a binomial distribution. But P, the proportion of those who agree in the population, is unknown. Now, the binomial distribution assumes certain things, not only just the proportion, but among these n people, we are assuming that their view will not influence one another. Suppose I agree, and then my family member may act independently of my view. All right, but this is also a little bit arguable. All right, but generally this is especially if you looking at unrelated individuals, chances are that it is a reasonable assumption. So this guy believes that the yield per acre of a variety of wheat is approximately normally distributed. So this is what he is trying to model. But the mean mu and the standard deviation sigma of the yields are unknown. Okay, so he wanted to estimate the mu and he wants to estimate the standard deviations. Now, if you wanted to challenge whether it is normally distributed, this will be another statistic problem. There are statistical procedures to test whether the underlying distribution is normal. All right, so but we will not do that in this course. Okay, population and sample. The totality of all possible outcomes or observations of a survey or an experiment is called a population. For example, I'm interested to find out, among the voters, those that are eligible, say in U.S., how many of them would like to vote Donald Trump, right? So I wanted to have the proportion here. And in this case, the populations will be all those who are eligible voters. But one may also argue, this is difficult questions in the actual social work, in the social science, because in U.S., voting is not compulsory. So even though you are eligible to vote, the population that actually will vote may be different from those that actually who are eligible to vote. So if you are just surveying people who are eligible to vote, then you are just finding the proportion of people who are eligible to vote, how many of them will actually vote Donald Trump. But if you restrict yourself for those that are likely to go for the vote, then the proportion would be closer to what you wanted to answer for the next election. So defining what is a population can be tricky itself, but this will not be our concern in this module because we are going to stay on a very academic side. But in actual applications, this is a problem in itself, and people need to, spend enough time to talk about this. I think I have mentioned to you that about the Coca-Cola survey, and the population that they are able to estimate are those that are, they are acceptable to the new Coke, but they haven't found out the proportion of people who are willing to give up the classic Coke, all right, instead of the new Coke. So there are very little details that are very important, but this is not our main concern. It will be a module in itself on sampling survey. So every outcome or observations can be recorded as a numerical or categorical value. Numerical will be when your measurement is a continuous variable, for example, height, weight, age, and so on, or length. Categorical, there are two versions. I mentioned it. There are basically two kinds. One is what we call ordinal, 1, 2, 3, 4, 5, like shoe size. The 1, 2, 3, 4, 5 actually tell you about the order. 5 is less than 6, so on. The other one is what we call nominal. For example, male and female, you use 0 or 1 to denote it, or low risk, medium risk, or high risk, you use 1, 2, 3. But this is more likely to be ordinal in that sense. But you can say young people, married people, old people, then there are 3 categories. We assign 1, 2, 3 to it. So the population can be finite or infinite. All right. In our module, we basically either assume it is infinite, because basically we will reduce ourselves to sampling with replacement. But we will mention a little bit about sampling without replacement. This is, again, mathematically much more challenging when you are dealing with sampling with replacement and the population is finite and it is not very, very large, maybe a few thousand, then that would be difficult. A finite population consists of a finite number of elements, so I think this is pretty obvious. Example of finite populations, even though the number can be very huge, students from this lecture group, so we are talking about 490, all the books in the central library, that would be a much bigger number. Now, of course, this is easy to say, then really the definition of a book is another problem. What constitutes a book, right? A small monograph, is it considered as a book or a thesis, a master degree, MSc thesis, or is it considered a book? Something like this. Or magazines, do you consider as a book? So the CAP score of students in NUS, so we are talking about maybe 20 to 30,000 people in NUS. So an infinite population is one that consists of an infinitely many number of elements. Now, infinity can be classified into many kinds. Two broad classification is countable, meaning that 1, 2, 3, 4, 5, you can enumerate them. All right, and uncountable, you can't there are so many that you can't even enumerate them. So some examples are here. Numbers from 0 to 1, this is known after the 18th century that this is infinite and uncountable. You can't count it. the proof was due to Cantor, all right, Cantor. There are infinitely many of them. You can't enumerate them. This is the number 1, this is number 2, and so on. The depths of all conceivable positions of a lake, the PSI level in the air at various parts of Singapore. Okay, for infinite population, it is impossible to observe all its values. So, and that basically forces you to do sampling. Some finite populations are so large that in theory, we assume them to be infinite, such as the populations of lives of a certain type of storage battery being manufactured from a factory. So it may be impractical or uneconomical to observe all its values. Okay, so there are many sampling schemes, and it is a subject in itself. The whole idea of sampling is to collect samples that are representative. For example, if you want to know whether people like a certain kind of bubble tea, you might suspect that the proportion of people who like it might change, might vary according to the age. So if you go to Ion or Wheelock Place and then survey it, unless you're going to set up a store around there, so it might be meaningful. But if you suspect that this is less popular among the older people, then but you are going to set up stores, a lot of chain stores in all over Singapore, then you might want to find out what is the sample that will represent where you are going to set up your store. So we will focus on what we call simple random sampling. There are a lot of beauty about this sampling scheme, but there are also many technical problems later on. I might mention some as if we have a chance. But then this is not the only one. You might have what we call a stratified sampling scheme, but of course you have to know the structure a little bit more. A stratified one might be like, for example, you want to find out the proportion of people who might like certain things. And if you do a random sample, you might have to go around all over Singapore to do so. But if you stratify it, say, according to HDB block, because you have some information about how many people stay in this few blocks, then you can do it in a stratified manner, all right, versus those who don't stay in the HDB blocks. So you have the proportion, you know something about the populations, and then you stratify them according to different strata, and then you do sampling of different stratum, and then somehow mathematically you can combine back all this. Okay, each observation in a population can be considered as a value of a random variable having a certain probability distribution function. So simple random sample. A simple random sample of n observations is a sample that is chosen in a way that this is the key. Every subset of n observations, so if you decide your sample size to be n, has the same probability of being selected. So my example of, you want to know about everyone, but then you only go to Ion or Wheelock Place area. So not everyone has the same probability of being selected in your sample. The older people will not, will be less likely to be selected because they don't go to this place as often as the young people. So as a result, that sampling will risk not being a simple random sample. We want to choose a simple random sample of size 5 from a group of 20 mice to be used in studying the growth rate of tumors in a cancer research experiment. Now this is the best way to do it. If you have, we label all the mice 1 up to 20 and then use a computer to generate 5, all right? Because if you are not relying on some computer or something impersonal to choose it, or you depending on you look at the individual mouse. I mean, oh, this mouse looks very sick. I might want to pick it. I mean, because I want to establish that exposure to this kind of toxin is likely to cause cancer. So you input your own bias into your selections if you want a certain result to come out, right? But this is really impartial because you use a computer to generate the numbers. Now, this is easy to say than it is actually done in actual situations. Back to the Singapore population thing again. Now, ideally, if I have access to the national citizenship record, I can label them 1 to up to, say, 5 million. And then I use my computer to draw 2005. But you will not be able to access the database in the first place. No one let you do that, all right? Even suppose you want to assess the NUS students, if you might want to try asking the registrar office. I don't think they would entertain you, all right? Okay, so this is easy to say, then it is done. I mean, if I do have the population, the whole list, all right? So this is how it can be done in R. Now, you sample X. X is this is the populations. You think of it as a hat. The hat has the number 1 up to 20 tickets, all right? And then you randomly pick 5, all right? So here, the first one you pick is 2, and then 20, and so on. But we are not going to be interested in the order that they are appearing. Now, there is an option in the R command is called sample X5. And the default is if you do not say it, then they would assume you are sampling without replacement, all right? So if you want it to be with replacement, meaning that the same mouse might be picked again, of course this is unlikely, I'm unreasonable in this example, then you have to have an option here, comma, replace, you have to spell it out, and equal to true, all right? So you allow a certain mouse to be lucky enough to be selected more than once. Okay, sampling with from finite populations. So suppose I only have 4 of them, and so I will be able to pick 2 from all of them, all right? So these are all the 6 possible samples of size 2 if we do sample without replacement. And since the order of the letters is disregarded, all right? Okay, sampling without replacement. So that is n choose n. That is where your first chapter is about. And if this is a simple random sampling, then every sample, there are n out of n are equally likely. So I have 1 out of n choose n. Okay, now if this slide is about sampling with replacement, so you can choose a particular one more than once. So as a result, you have the first choice, you have 4 ways of doing it, and then the second way, the second step, the second person you want to choose will also have 4 ways. So it's 4 times 4, all right? And here we regard A, B, and BA are different. For example, you are picking from amount 4 to receive 2 cash prize. One is 100 and then the other is 50. Then the order is important, all right, here. Sampling with replacement, in general, there are n to the power n samples of size n that can be drawn from a finite sample of size n, big N, with replacement. So even when n is moderate, suppose n is 1,000, and then if you decide to choose 20, this number is, really, really huge, right? Okay, sampling from infinite populations. When lists are available, I think this is the key here. When lists of the subjects in the populations or the items are readily numbered, or available first. It is easy to draw random samples from finite populations. Now this is, again, it overlook one little technical things. Even if you are able to draw out whom to survey in Singapore, if you don't have their phone numbers or contact numbers, I mean, you are going to have some difficulty to hunt them down, right? So unfortunately, it is often impossible to proceed the way we have just described for an infinite populations, or when the list is not available. All right, the concept of random sampling from an infinite population is more difficult to explain, so we don't need to explain. We shall use examples to show the characteristic of such a pop sample. Suppose we consider the results of 15 tosses of a coin of a sample from a hypothetical infinite populations, which consists of the results of all possible tosses of the coin. I think this is not a very good example because it is not an infinite population, because it's, there are only 2 to the power 15, so it is not even close to 1 million. So, the population is actually finite, all right? We would be sampling from an infinite population if we sample with replacement from a finite populations, all right? One example, which is what I was considering, this example seems to be very innocent, but this is the case. Sampling a number from 0, 1. This is maybe $1 million kind of a question, in a way that every number stands the same chance. Because if you are able to sample it in a uniform manner, that is to say, in a uniform distribution, then you will be able to generate a normal distribution. All other distributions, if you are able to generate a random number, really random, all right, from 0, 1, then you will be able to answer all kinds of other problems. So right now, the random number generator is basically using modulo mathematics. And this is, the modulo mathematics is actually deterministic, all right? So it is not random in that sense. There is some kind of a randomness, but not the kind that we are thinking of. Okay. Okay, so maybe I will talk about this after the break. Let's have a break first. So let's come back at 10:52. All right. I wanted to cover as much as possible. So this example is trying to verify certain probability. Now this is actually calculated based on probability argument. But suppose we do not know how this probability are, we can actually use sampling, or in our previous word, we are using simulations. So one way to do this is to do this. So I sample from the back. The back is 1 to 6. So this is a shorthand notation. If you don't like it, then you just write down the list, 1, 2, 3, 4, and up to 6. All right. This is okay because there are only 6. But if you are talking about 100, it needs a little while to type it. So so this might be more instructive. This is the shorthand notation for R. And then you are sampling it 2 times. So you draw, you have a hat with tickets 1, 2, up to 6. You draw it 2 times. And then you have to tell the sampling scheme is to sample with replacement, because this is going to be the same as rolling a die. So when you roll a die, the number that you get might also be qualified to be rolled right for the next time. So it's the same as putting back the number you get from the hat in the first time, and then you redraw it. So this is it. So this time I have 5, 6. And if I were to do it, I have 5, 2. So this is the situations here. But this is not the outcome that I'm interested. I'm interested more in adding them up. So I sum it. Okay. So I have a 9. Sorry. So I have a 4. And I have a 8, and so on and so forth. Now, so what I'm going to do is to do it in a large scale. So because we know the number is something to do with 36 in the denominator, so to get some round number, so it might be better that I'm going to roll it 36,000 times, all right? And so if that is the case, I would be expecting 6,000 times for 7, all right? So this is what I'm going to do. So I first create a vector which is 36,000 long, and I've temporarily fill them as 0, and I'm going to replace the actual number. And now I'm doing it in a loop. So so when k equal to 1, that corresponds to my first row of the pair of the die. And then I do it for step 2, so that would be A2. So this is where A is a list, and then square bracket K means where you're going to put it into the, it's more like the address where you put it in. So I'm going to do the sampling, and then something that I just did, and then I add them up and put the result into the K component of the list, all right? So this actually can be done very quickly, 36,000 times. And then we can form a table of this. Now because they have been replaced, the 0 have been replaced by the sum of each of the row. So for 7, it is very close to 6,000. But I wanted to emphasize this, you don't get the 6,000 exactly. You always have some kind of a chance variations. Now, if I were to repeat it again, so now currently my A consists of all this sum, but now I'm going to replace them again. And if I were to make a table, you will see that now the number of times that I will get 7 is not 5,982, but now it's 6,160. All right. Now there will be some way to make a guess whether you are massaging the numbers. Some people don't do the simulations and then they create the simulations in their head. All right, and so they might write 6,000 or 6,005 or something like that. Then the answer is too good to be true. All right, so there is some way to assess it. Okay, so if you want to fake your simulations, there will be some way to detect it. Okay, now to basically now we are doing it for 100 times. So for the first 100 times, maybe I can show you what the first 100 times look like. So 1 to 100. So these are the numbers that I actually get in my second time of the rolling the die 36,000 times. So my first time is a 3 and then a 6 and so on. Now, why do I wanted to spend time on this? Because I wanted to explain two things. One is I use an uppercase to denote the number that I will get in my first roll of the pair of the die. This is before I actually roll it. Okay, so the number that you get is random. All right? Is that all right? Because this is, I haven't rolled it, but I'm denoting that this will be the first sum I get. X2 will be the number that I get, or the sum that I get in rolling the pair of dice the second time. Okay, and this is 100. Now the small x here, sometimes we call it realization. So this is actually after you roll it, you get the numbers. All right, so this is a realization of my first roll of the pair of the dice. I get a 3. All right, so it probably comes from 1, 2 or 2, 1. We do not know which. All right, so so it makes sense to talk about probability because here this is the formula or the random variable that you will get in your first roll. Okay, you haven't rolled it yet. You can think of it, and this is what you roll after you roll, and you get this. Now, suppose we have two of you doing it in a similar manner. One of you will get x1, and then the other one will get y1. All right, because unless they copy one another, I mean, again, this is not supposed to be. So it would have a distributions. Okay. Now this take a little while to sink in because all the statistics is based on what we call the likelihood functions. So this is going to be the case. Now let x be the random variable with probability distribution or probability mass function or density functions. And let x1, xn be the n independent random variables, each having the same distribution as x, because you are doing sampling from the populations. So the population has a specific distributions. So each of the item or each of the values from your sample will obey the distribution from the populations. So we call this as a random sample of size n from a population with distribution. All right? And the joint probability mass or density function will be given by this. Now this is actually assuming independence of each of the draw. All right? So what you get from your first reading will not affect you how to get the second reading and so on and so forth. Now the independence is actually built into the assumption, but in reality, when people do survey or sampling, they actually, it's very difficult for the interviewer to exercise this kind of independence unless the person has already been given the list, exactly when to ask the persons or whom to ask. Because when you are really doing a face-to-face survey, this guy looks fierce, then maybe the next one. I mean, so you are choosing your subjects, all right? For example, when you try to interview a guy, but the guy is actually he is having a date, right, with his girlfriend, then you stop him, and then he probably will say no. I mean, he has more important things to do. All right. But this is the basic theory or the basic assumptions of random sampling, meaning that each of the values are coming from the populations, and then the outcomes of this or each of the random variables are independent of one another. All right, so this is our independent, identically distributed situations. A sampling distribution of sample mean, this need a little bit of thinking, because recall that our main purpose in selecting random samples is to draw information about the unknown population parameters. So we will form something like what we call a summary statistics, like the sample mean and so on, and use the sample mean to estimate the population mean. All right. So this is what we are going to do. For instance, suppose we wish to know the proportion of people in Singapore who preferred a certain brand of coffee. A large random sample can then be selected from the population, and the proportion of this sample favoring the brand of coffee in question is calculated. All right? The value is now used to make some inference concerning the true populations. Now, the basic assumption of all our subsequent calculation is that the sample is done properly. All right. If the sample is not done properly, then that would be, doesn't make sense to do the calculations. So a value computed from a sample is called statistic. That is the word statistics without the s. All right. So it is singular here. But the subject is called statistics with an S. Okay, so since many random samples are possible from the same populations, we would expect the statistic, the number that you calculate from one particular random sample, to vary somewhat from sample to sample. So hence, a statistic is a random variable. This is crucial to recognize it. It is meaningful to consider the probability distribution of a statistic. It is because the value of the given statistic, let's say you take the average of all the numbers you get, this is a statistic. This is called the sample mean. But when you really do your collections of the sample, so you will, according to your formula, you will have a number. But suppose another guy is repeating the same sampling, not the same sample, but repeating the procedures of drawing the sample, he might get slightly different n numbers, and as a result, his mean will be different from your mean, all right? And so there is some variability of this, and we should think of it as a random variable. So I think we have some numerical examples to illustrate the idea. The probability distribution of a statistic is called a sampling distribution. All right, sample mean. So this is the one that we use. Now, let me repeat our notations. We use uppercase to denote random variables, values that you haven't observed yet, but indicate this is the first value you are going to see, and this is the last value you are going to see, all right? And this is the formula that you are going to compute, okay, even before you have done the sampling, all right? So this is the general formula that you are going to use. So this in itself is a random variable, all right? Or these are all random variables because you haven't observe the value yet, all right? So think of calculating the sample mean is a procedure. This is a good analogy. The actual sample is not yet collected, all right? Xi denotes the value of the first sample observations, and then Xi is a random variable. So are the X2 up to Xn, and as a result, X bar, the bar is on top, is a random variable as well. Now this is our notation here, but if you want to emphasize that it is of sample size n, some people put a subscript n here, but still keep the bar on top because they wanted to tell you that this is the sample mean coming from a sample of size n. All right, so if they want to emphasize this. Now to study the sampling distribution of the sample mean, we consider this as an example. Each one is equally likely. So I'm picking an odd number from 3 up to 11, inclusive of them. So each one has a probability of 1/5 to be chosen. And the population mean and population variance can be found by this. All right. This is because you just the population mean is actually the center of gravity, but because everyone is having the same probability, the center of gravity would be the middle part of the number, so which is 7, and you can calculate the population variance here. All right. So actually we know it because, but we want to illustrate a point. Okay, suppose we list out all possible samples of size 2. All right. So this is an illustration. So for example here, the first number you draw is a 3. The second number you draw is also a 3. All right. And when you calculate the mean of the sample, it is 3. But in another instance, you might get a 3 for your first draw, and then a 5 for your second draw, and the mean will change to 4. All right, and so on and so forth. Here we list out 5 choose 2 is how many? Is 10, right? 20, right? Okay, no. But I allow replacement, so it is 5 times 5. So I should have 25. All right. Okay, how many are here? 1, 2, 3, 4, 5. So there are 25 of them. So this is a complete list of the whole thing. So these are all the 25 possible samples that you can get. And these are all the 25 possible mean that you will get from the procedures. All right? And so the sampling distribution, now you do a count. Out of the 25, you have how many 5? You have 3 5s here. And so this is how we form the table. All right? Now this is, of course, it's more like an academic exercise to illustrate the point, but we painstakingly enumerate all the possible cases in this table, and then from which we can form this table for the probability distribution of the sample mean. All right? So this is the sample mean probability mass distribution, density, mass function. All right? And as a result, now I can compute the mean. So the way to go about it is 3 times 1 over 25 plus 4 times 2 over 25, and so on and so forth. And you can verify that this is equal to 7. This is not a coincidence. The sample mean will have the mean of a sample mean is equal to the population mean. This is a mouthful. So mean of a sample mean equal to the population mean. Now this is not always the case, all right, but no, this is always the case, but this is only for the mean. For other characteristic of the distribution, let's say the variance will be different. The population variance is what? Is 8, but here the population variance is now half. And in fact, this is the effect. when you do it 2 sampling, the effect will be half. And if you do it 4 times, the effect will be 8 divided by 4. All right? So the reason of this is because there are occasions, 7 is your mean in your population. And sometimes the first one, there is a tendency for you to be on the right side of the population mean. You get something bigger than the population mean. But the second time when you get it, there is a possibility that you get it on the left-hand side. So as a result, when you take average, now you actually get closer to this because one number is an overestimate and then another number would be underestimate. And so as a result, when you average them, it is nice, all right? So cancellations. And that is the whole point of doing sampling because very often, of course, 2 is difficult because sometimes you might have probability of 1/4 to have both of them are on the right-hand side or both of them on the left-hand side. But with probability half, one is on one side, the other is on the other side. So you actually shrink it, all right? So there is an idiom, right, called measure twice and cut once. That is actually the idea. So, so this is not specific situation, but we do have this. So this is a conclusion. The mean of the sample mean is equal to the mean of the populations. All right. So watch out, the bar is here on the left-hand side, and then there is no bar here. All right. And here the variance of the sample mean, the x bar, is equal to the population variance divided by n. So that is why people are interested to do a larger sample size, because now your variation is very small. That means the number you get is likely to cluster around 7. Okay? Because the variance here is measuring the spread. So if your spread is very small, your sample mean, you are not going to do it many times. You are only going to do it once. But if the variation is small, with a very high chance that it will be clustered around the 7. So that is the idea. The result, which is marked in red of the previous example, is a general root true. So I don't know whether, okay, we state it as a theorem. So for random samples of size n, this is the big assumption here, random samples, right? Okay, of size n, taken from an infinite populations or from a finite population with replacement. Okay, now very often we are not going to replace the things that we are going to pick. But we assume the population, even though it's finite, is reasonably large as compared to your sample size. Suppose your sample size is 1,000, but you are picking it up from 1,000,000. So it's not going to make a big difference because it's unlikely that the same guy is actually being chosen again. All right. So having mean μx and then this. All right. So this is referring to the populations. Watch out. All right. So this is about the populations. And now the sampling distribution of the sample mean has this. Now we are not telling you what the distribution is. We are just telling you the distribution has this mean. All right. The mean of the sample mean is the same as the population mean. And the variance of the sample mean is 1 over n times the variance of the populations. So this might be easier to read here. So the sample mean has these nice features that on the average, the sample mean is the same, coincide with the population mean. If this is one of the things that you are interested to find out, then it means that you are not off, okay, on the average. Okay, the law of large numbers. Now, if you Google it, there are 2 distinctions. One, this is actually people qualify as the weak law of large number. All right. So if x1 up to xn be a random sample of size n from a population with mean mu and finite variance sigma square, then the probability that your sample mean deviates from your target okay, this is your target, you want to know it, exceeds a certain tolerance, you set it yourself. Say, for example, I can't stand it when the error is, say, 0.1. So the probability that your sample mean deviates from the actual mean that you are trying to measure bigger than 0.1, let's say, it will go to 0 if your sample size is increasing to infinity. All right? This is only a qualitative statement. I mean, of course, this is a difficult. This result is due to Chebyshev. All right. So this is the weak law of large number. But qualitatively, it says that now the nice thing is epsilon. This is not quite true. Epsilon has to be positive. Okay. So cannot be negative. If it's negative, this is always 1, right? This can't be, this is always true. Then this will be 1. So we need to change this here. Okay, so please change it then for any epsilon positive, all right? All right, so this is a mistake here. Okay, so basically you have a tolerance level. You can't accept the fact that this is what you will get deviates from your target by a certain amount, and how much this amount should be depends on the problem. All right. Now, in fact, we have a better way to state this. Okay, but let's have a remark first. This says that as the sample size increases, the probability that the sample mean differs from the population mean goes to 0. Okay, another way of looking at this is that it is increasingly likely that X bar is close to mu if your sample size is getting larger and larger. Okay, so the sample mean thing, to estimate the mean of a population, a very good candidate is the sample mean, and it enjoys this property. And in fact, something stronger can be said. All right? Okay, so this is this. X1 up to xn be a random sample from this. So this is for illustration purposes. Then expectation of x is equal to 1/2. And the variance is equal to 1/12. So this is, I think we have mentioned it before, but we actually do it for uniform AB. So if you remember, that would be A plus B over 2. And then this would be B minus A squared over 12. So now A is 0, B is 1. So we can set that. And if N is 3 million, of course, unlikely we are going to do this kind of sample. And epsilon is 0.01. Then we can calculate something. The xn bar of the sample mean will have a sample of size this. So this is this. But now the variance is almost like 0 because of the size that we choose. So that means if you conduct it once, but this once is really huge, the sample size is 3 million, then you will almost get half, all right? You can use R to do that in this case, and then you will get something like this, all right? Now, we consider what is the likelihood that it disappoints us. We want it to be close to 0.5 within this amount. And this is something that is outside our expectations, all right? And so as a result, this is using the Chebyshev inequality. And so I will have this. And when you work it out, so I think this is a good exercise. And it is very easy to do that. So the answer is only about 3% of the time that you deviate from half the one that you are targeting by 0.001, all right? So you have fairly accurate calculations. So that means your estimate is something like either below 0.499 or above 0.501, all right? So you are very, 97% of the time you stay around 0.4999 and 0.5001, right? So that is very nice, all right? Okay, central limit theorem. I think I will, let's just go through some of the qualitative part here, all right? I have mentioned that this is the, definitely this is one of the most important theorems in probability. But when it was entirely formulated in 1930, after the efforts of, over probably 1 or 2 centuries, it is finally settled. So this theorem in the probability area thinks that this is the theorem that you should know, and this is the central limit theorem. Okay, so this is the statement here. X1 up to xn be a random sample from a population with mean mu and a finite variance sigma square. So I make no assumptions about the populations. I only assume that it has a finite mean mu and a finite variance sigma square. Now, it might seem that I'm saying something that the condition is not always true. It is because in our module, we do not show you something that does not have a mean and something that may not even have a finite variance. So as a result, these are important. So we need 2 moments, the first one and the second one. And this is all we need. We don't need to assume anything further. The population distribution can be discrete, can be continuous, can be any shape, all right? But now, if you look at the sample mean xn, which is, and then if you standardize it, all right, subtract the mean mu, and then divide it back by this. Now, why do I have a sigma over square root n? Because I'm dividing this, the variance of the standard deviation of the numerator. The standard deviation of the numerator is actually the square root of the, is the square root of this, all right? So when you take the square root, so you have this will be sigma, and this will be square root n. So that is where it comes from, all right? So you have to have an extra factor reflecting the fact that your mean, the sample mean actually shrink the variation by n-fold, all right? Or equivalently, now this is not a, we add in the word approximately, okay? So not only it is very close, but the thing is now getting more and more bell-shaped, all right? So this is what the, and I think when you are learning it in your A-level or your IB or whatever, people usually give you a rule of thumb 30 or 35 and so on. This is rather arbitrary, all right? So the central limit theorem states that under rather general conditions, it is really general because in almost all data analysis, the mean and the variance of the population would exist, all right, and finite. And for large n, the sum or the mean of a random sample drawn from a population is approximately normal distributed. So the whole theorem say it is almost normally distributed. Okay, and that indicates the importance of the normal distributions. And that is why normal distribution appears everywhere. Now, one of the things is like, I think some of you did a bit of science in your A-level. You might have heard of Brownian motion, the pollen grain on the water, and it is actually observed by a botanist, Brown, that is starting around. And people start to try to model that. I don't know whether Einstein was the first one, but Einstein used, people try to explain why the pollen grain move in a very haphazard way. It is because you only see the motion of the pollen grain, but in fact the motion is actually come from a result of a lot of bombardments of the water molecule in the medium of where the pollen grain is. And now, so the movement of the grain at a certain moment is due to the sum of all these forces on the grain. And so that movement will be following a normal distribution. All right? A two-dimensional normal distribution because it is on the water. Now, Einstein actually made use of this. I don't know whether he actually modeled it but he made use of this. He actually determined the number of Avogadro number. So this is one way to estimate the Avogadro number for 1 mole of something. All right. So and this is why in a lot of situations we assume something is bell curve. For example, in a test or in an exam paper, where the exam paper have a number of questions and then a number of parts. So your final grade is actually the sum of many, many parts and many, many questions. So as a result, very often we observed a normal curve. But suppose you are taking an exam from, say, arts, and usually they just give you 1 or 2 questions, and then you have to write pages and pages for that. Now, it depends on how the guy is giving you. I mean, if he only quantized the mark like 0, 5, or 10, then you have only 2 questions. You only have 0, 10, 5, and 10, the combination. You either get 0, get 5, get 10, 15, or 20, or right, something like this. So this will be far away from normal distribution. So it is because in modeling it, you have to recognize that the number you are getting is actually a result of many, many small factors. And each node, there is no dominating factor. And they contribute in totality that result from this. For example, our height or some of our biological feature is actually a sum of many, many other factors. For example, our height. Genetic is the most important thing. Other than that, is your nutrition or the way you grow up and what kind of things that you like to do. So it contributes in small parts and determining, in some way, determine your height. All right. Okay, so the rule of thumb, in practice, the normal distribution provides an excellent approximation to the sample distributions of the mean x bar if n is bigger than 30. So if the sample size is 30. So this is the rule of thumb. I don't know Kuhl's rule of thumb, but you might have heard someone say 35, another guy is 25, and so on. So for some distributions, the sampling distribution converges quickly to normal, even for small n. The next slide will show you some example. For the same sample size, the more symmetric, this is crucial, the more symmetric the distribution of the population, the better is the approximation. So if you have some idea that the underlying population is symmetrical around the population mean, then your 30 would be a very good requirement. You can even go down to 20 or 25 or whatever. All right. So this is the something that you can try. All right. Okay. So this is this. Now let's look at the top panel. This distribution is entirely symmetrical, and so is this. All right. But whereas this is especially skewed. All right. And you will see when my sample size is 2. It is actually quite like triangle. This is a triangle. And when n equal to 5 here, this is already having the bell shape. And when n equal to 30, we should do a little bit more, 10 or 15. But you can see 30 is really nice. Almost like bell shape. We can actually draw the normal curve on top of it, and then you will see, all right? But you will see for n equal to 5, it is really nice already. And similarly, for the third column here, when n even is small, it is very nice. I mean, it's almost like bell shape. So your rule of thumb 30 is probably too strict for symmetric distribution. But here, in the middle one, the underlying population is very skewed. It's not even symmetric. I mean, so far away from being symmetry. You will see the first thing they wanted to do, if your sample size is keep on increasing, is to correct the skewness. Okay, so you can see this is a little bit less skewed than before because you have a bit of a lump here rather than entirely going this way. And then when n equal to 5, this part is now getting a little bit more. So as a result, you have closer to the bell shape. And then when n equal to 30, so this is still quite like a bell shape, all right? So I will stop here. In order to determine the recommended sample size, this is not a simple question. So the rule of thumb is actually a guideline, all right? And if your underlying distribution is very skewed, you need a larger sample size with the hope that a larger sample size will correct the symmetry, or the not symmetric, because the underlying normal distribution is symmetric. So you need to gradually move it so that it would be symmetric. All right, so you need a larger numbers. But you already, if you start with something that is symmetric, you don't need to have these corrections. Okay, so maybe I'll stop here.
For this one, right, how come when n equals to 2 and like n equals to 5, right, there's still like so many points?
Yeah, shouldn't there be only 2?
I thought it's
he is doing it. I don't know. I mean, did he say it? He do it maybe 5. I think he might have the R code. Right? He didn't include it here, but in the R code file.
So it's like, is it like a table like this?
Yes. He's doing it for maybe 5,000 times or something like that.
So it's like this table lah. Like he only like n equals to 2. So
No, it's somewhat like this, somewhat like what I did here.
Oh, okay.
So I do it 36,000 times.
Also,
Then he plot the histogram of this.
So
okay.
36,000 times.
Yeah.
This is what I said.
Oh,
Yeah.
Just now when you were going through example 5 with the
Yeah, here, right?
not here, the one from